Have you ever wondered why your favorite graphics program on the Macintosh can't run on Windows? Why can't that game you have so much fun with on your iPhone be found on your Android tablet? Why can't that project you spend so much time designing and building no longer works with the newest version of your operating system? Hello, my name is Jim Mooney. I recently retired after teaching computer science at West Virginia University for 35 years. And these are questions I've studied and taught about for much of my career. For the last 8 of those 35 years, I was the director of the Lane Department's Software Engineering program at WVU, a role now filled well by my friend and colleague Dale Dazilski. For many years, I also taught a unique advanced course called Developing Portable Software, CS533. In addition, next year I'll begin to teach one of our more important core courses, SENG 520, Software Analysis and Design. More about these courses shortly. First, I'll tell you a little bit about myself. My educational journey took me through Notre Dame and Ohio State for a Bachelor of Science, Master of Science, and finally PhD in what would today be called computer engineering. My first programs were written in Fortran and ran on a UNIVAC 1107. Other computers I worked with during my schooling included the IBM System 360 and the digital PDP-8 and PDP-9. The PDP-8 we had in the EE department at Notre Dame was especially interesting. We could touch it, take it apart, and program it any way we wanted to. Of course, all programs, including system programs, had to be loaded from punched paper tape, which was prepared beforehand on a separate teletype machine. For a year, I was the sole system manager for the PDP-9 in the EE department at Ohio State. This was a more advanced system storing data on special magnetic tapes. I spent some long nights keeping both the hardware and the software running. One of my proudest achievements was finding a bug in a company-supplied arithmetic routine and patching it without using a single extra word of storage. We sometimes made time on our PDP-9 available to local entrepreneurs. One pair came in regularly for a while as they waited for their own computer to be delivered. They were doing some preliminary design work for their new company called CompuServe. When I reached all but dissertation status, ABD, I left school and worked for several years for a company near my home in New Jersey that made typesetting equipment for newspapers. They were designing their first computer-driven typesetters, and I was their first programmer. In those days, there were dozens of types of mini-computers in use, all with unique architectures. We used a mini-computer designed by a local company called the GRI 99. All programming, of course, was in assembly language. After a few years, our company merged and became larger and moved to the Boston area. We now worked with different mini-computer types, and I became responsible for operating system development. I began to wonder why operating systems had to be so different and how these differences kept applications from being more portable. When I finally finished my dissertation, I decided to begin looking for an academic position. That search brought me to West Virginia University, where I've taught since 1979. Not long after I arrived, I attended a research conference and wandered into a meeting that sounded interesting. They were working to build a standard for operating system interfaces so programs could be more portable. I joined this group, eventually became the chair, and was drawn into the world of computing standards. This led to a focus on standards and portability that has continued throughout my academic career. At WVU, I have taught many courses, but my focus has remained in 3 areas: operating systems, computer architecture, and software portability. I co-authored a textbook on operating systems with my colleague, Dr. Malcolm Lane. For many years, this became the basis for our infamous undergraduate operating systems course. In spite of my retirement, I will continue to teach some courses in the software engineering program. I will teach CS533, Developing Portable Software, and now I will teach SENG 520, Software Analysis and Design. Let me tell you a little bit about these courses. To see the role of SENG 520, we should look at the role of each of our core courses in the basic curriculum. The key phases of a software engineering project generally include requirements analysis, design, implementation, testing, and ongoing maintenance. The success of such a project also hinges on effective project management. The WVU MSSE core curriculum is designed to provide an introduction to each of these areas. SENG 510, Project Management, addresses project management. SENG 520, Software Analysis and Design, presents requirements analysis and design. SENG 550, Object-Oriented Programming, teaches implementation. SENG 530, Software Verification and Validation, deals with testing and related topics. And SENG 540, Software Evolution, focuses on managing a software system through the maintenance lifecycle. The course I will teach, SENG 520, looks at the early activities of a software development project, requirements analysis and design. We also look briefly at the early history of software development and the factors that led to the emergence of the field of software engineering. Early software development was carried out in an informal, ad hoc manner. Programs were small, computing was for numerical calculations only, there were no high-level programming languages, and programmers were employees of the computer companies. A decade or so later, we had Fortran and COBOL, programs were getting much bigger, and businesses were depending on software systems to run their critical activities. Computers were also being used for critical control functions in areas like military and space programs. For these large systems, existing development methods were unacceptable. Bugs were rampant, programs were hard to maintain, and consequences of failure were high. For example, the Mariner 1 space mission failed because of a small typographical error in its software. The problems came to a head with the development of increasingly complex operating systems, culminating in the well-known OS 360, which eventually became the most long-lived and stable operating system ever. In its early days, though, it was a disaster. Years later, and loaded with bugs, this multi-million-line system was so unmanageable that it single-handedly almost triggered the birth of software engineering. Everyone agreed that such systems could not be developed in the same way again. In the introductory part of SENG 520, we examine this early history, along with the first ideas that emerged as the field of software engineering took shape. One important idea was to break down the overall process of software engineering into distinct phases. Although we have learned that we cannot always define these phases in exactly the same way or go through them in a completely linear manner, we do believe that before we can develop a solution to a problem, we have to understand the problem. We have to know what our system will need to do before we can figure out how to do it. This is the process of requirements analysis, the first phase covered by SENG 520. Requirements analysis is a challenging problem. If you are developing a system to solve a customer's problem, it is certainly a mistake to assume you know what the customers need or want. Often the customers themselves do not know or cannot fully explain what they want. There may be an iterative process of creating proposals, of developing prototypes, only to find out that what is really wanted is totally different. Feasibility studies are necessary because requirements may be unrealistic. Non-functional requirements such as performance or security must be examined. The end result, ideally, is a specification document agreed to by all, complete with operational models to show exactly how the system will behave. Unfortunately, situations and needs are constantly changing, so by the time the original requirements are pinned down in full detail, the current requirements may be quite different. When the requirements are fairly understood, it is possible to begin the process of design. This is a shift from considering what the problem is to developing ideas to solve it. This is not the time for writing code, although we may need prototypes to try out our ideas. Many key decisions have to be made in the design phase. Should our system be distributed, client-server, or peer-to-peer? Should we use an object-oriented approach? Perhaps an event-driven or functional design? The overall architecture needs to be developed, then gradually broken down into manageable pieces. In this process, the partition strategy and the interfaces that result may have a critical impact on the success of the project. These and many other design issues form the final part of our study in SENG 520. CS 533, Developing Portable Software, is an advanced course, the only course with a CS designation that is a full member of the software engineering program. The purpose of this course is to learn how to develop software that is more portable, that is, can be ported to new environments with lower cost than traditional software. We use the following definition for portability. A software unit is portable with respect to a given class of environments to the degree that the cost of porting it to a new environment in that class is less than the cost of re-implementation. There are some important points in this definition, including the idea that portability is a matter of degree, that it depends on the target environment, and that it must be compared to alternatives to evaluate its cost. We then need to dispel some of the myths of portability, including various ways by which many believe the problem has been solved, such as standard languages, like Fortran, Java, and Python, universal operating systems, such as Unix and Windows, universal architectures like Intel and ARM, software patterns such as UML, the Internet and the web, and many more. We then explore models of software system interfaces, such as this simple one from the U.S. Defense Department, and plunge into the complicated world of standards. With this background in hand, we begin a systematic study of portability strategies, culminating in a large classified collection. We then explore how to map these strategies into the various phases of the software engineering process. Our definition of portability is very broad. With this in mind, we look into a number of ways to make our software adaptable, such as internationalization, adaptation for the disabled, economic portability, that is, running in less capable environments. Finally, we look into some portability issues for application areas that may seem inherently hard to port. These include parallel high-performance applications, real-time systems, and of course, in today's world, mobile environments. Finally, oh yes, there is a project. Over the course of the semester, you will develop several versions of a program in your favorite language, ported to several different environments. If you are trying to avoid courses that do actual programming, you probably should not take this course. That about covers who I am and what I do. I hope to see you in one of my classes. Please feel free to contact me if you have any questions.